The Foundations of Geometry by David Hilbert. Chapter 3, The Theory of Proportion. Section 14, Demonstration of Pascal's Theorem. In this and the following chapter, we shall take as a basis of our discussion all the plane axioms with the exception of the axiom of Archimedes. That is to say, the axioms group 1, 1 and 2, and the axioms of group 2 through 4. In the present chapter, we propose, by the aid of these axioms, to establish Euclid's theory of proportion. That is, we shall establish it for the plane, and that independently of the axiom of Archimedes. For this purpose, we shall first demonstrate a proposition which is a special case of the well-known theorem of Pascal, usually considered in the theory of conic sections, and which we shall hereafter, for the sake of brevity, refer to simply as Pascal's theorem. This theorem may be stated as follows. Theorem 21, Pascal's theorem. Given the two sets of points A, B, C and A', B', C', so situated respectively upon two intersecting straight lines that none of them fall at the intersection of these lines. If CB' is parallel to BC' and CA' is also parallel to AC', then BA' is parallel to AB'. In order to demonstrate this theorem, we shall first introduce the following notation. In a right triangle, the base A is uniquely determined by the hypotenuse C and the base angle alpha included by A and C. We will express this fact briefly by writing A is equal to alpha C. Hence, the symbol alpha C always represents a definite segment, providing C is any given segment whatever, and alpha is any given acute angle. Furthermore, if C is any arbitrary segment, and alpha and beta are any two acute angles whatever, then the two segments alpha beta C and beta alpha C are always congruent. That is, we have alpha beta C equals beta alpha C, and consequently the symbols alpha and beta are interchangeable. In order to prove this statement, we take the segment C equals AB, and with A as a vertex lay off upon the one side of this segment the angle alpha, and upon the other the angle beta. Then, from the point B, let fall upon the opposite sides of the alpha and beta the perpendiculars BC and BD respectively. Finally, join C with D, and let fall from A the perpendicular AE upon CD. Since the two angles ACB and ADB are right angles, the 4 points A, B, C, and D are situated upon a circle. Consequently, the angles ACD and ABD, being inscribed in the same segment of the circle, are congruent. But the angles ACD and CAE taken together make a right angle. And the same is true of the two angles ABD and BAD. Hence, the two angles CAE and BAD are also congruent. That is to say, the angle CAE is congruent to beta, and therefore the angle DAE is congruent to alpha. From these considerations, we have immediately the following congruences of segments. Beta C is congruent to AD. Alpha C is congruent to AC. Alpha beta C is congruent to alpha of AD is congruent to AE. Beta alpha C is congruent to beta AC congruent to AE. From these, the validity of the congruence in question follows. Returning now to the figure in connection with Pascal's theorem, denote the intersection of the two given straight lines by O and the segments OA, OB, OC, OA', OB', OC', CB prime, BC prime, CA prime, AC prime, BA prime, AB prime by lowercase a, B, C, A prime, B prime, C prime, L, L star, M, M star, N, N star, respectively. Let fall from the point O a perpendicular upon each of the segments L, M, and N. The perpendicular to L will form with the straight lines OA and OA prime acute angles, which we shall denote by lambda prime and lambda respectively. Likewise, the perpendiculars to M and N form with these same lines OA and OA prime acute angles, which we shall denote by mu prime mu and nu prime nu respectively. If we now express, as indicated above, each of these perpendiculars in terms of the hypotenuse and base angle, we have the three following congruences of segments. 1. Lambda b prime is congruent to lambda prime c. 2. Mu a prime is congruent to mu prime c. 3. Nu a prime is congruent to nu prime b. But since, according to our hypothesis, L is parallel to L star and M is parallel to M star, the perpendiculars from O falling upon L star and M star must coincide with the perpendiculars from the same point falling upon L and M, and consequently we have 4. Lambda c prime is congruent to lambda prime b. 5. Mu c prime is congruent to mu prime a. Multiplying both members of congruence 3 by the symbol lambda prime mu, and remembering that, as we have already seen, the symbols in question are commutative, we have nu lambda prime mu a prime congruent to nu prime mu lambda prime b. In this congruence, we may replace mu a prime in the first member by its value given in 2, and lambda prime b in the second member by its value given in 4, thus obtaining as a result nu lambda prime mu prime c congruent to nu prime mu lambda c prime, or nu mu prime lambda prime c congruent to nu prime lambda mu c prime. Here again in this congruence we can, by aid of 1, replace lambda prime c by lambda b prime, and by the aid of 5 we may replace the second member mu c prime by mu prime a. Then we have nu mu prime lambda b prime congruent to nu prime lambda mu prime a, or lambda mu prime nu b prime congruent to lambda mu prime nu prime a. Because of the significance of our symbols, we can conclude at once from this congruence that mu prime nu b prime is congruent to mu prime nu prime a, and consequently that 6. Nu b prime is congruent to nu prime a. If we now consider the perpendicular let fall from O upon N and draw perpendiculars to this same line from points A and B prime, then congruence 6 shows that the feet of the last two perpendiculars must coincide. That is to say, the straight line N star is equal to AB prime, makes a right angle with the perpendicular to N, and consequently is parallel to N. And this establishes the truth of Pascal's theorem. Having given any straight line whatever, together with an arbitrary angle and a point lying outside of the given line, we can, by constructing the given angle and drawing a parallel line, find a straight line passing through the given point and cutting the given straight line at the given angle. By means of this construction, we can demonstrate Pascal's theorem in the following very simple manner, for which I am indebted to another source. Through the point B, draw a straight line cutting OA' in the point D' and making with it the angle OCA', so that the congruence 1 star, the angle OCA' is congruent to the angle OD'B, is fulfilled. Now, according to a well-known property of circles, CBD'A' is an inscribed quadrilateral, and consequently, by the aid of the theorem concerning the congruences of angles inscribed in the same segment of a circle, we have the congruence 2 star. The angle OBA' is congruent to the angle OD'C. Since by hypothesis CA' and AC' are parallel, we have 3 star. The angle OCA' is congruent to the angle OAC'. And from 1 star and 3 star, we obtain the congruence. The angle OD'B is congruent to the angle OAC'. And from 1 star and 3 star, we obtain the congruence. OD'B is congruent to the angle OAC'. However, BAD'C' is also an inscribed quadrilateral, and consequently, by virtue of the theorem relating to the angles of such quadrilateral, we have the congruence 4 star. The angle OAD' is congruent to the angle OC'B. But as CB' is, by hypothesis, parallel to BC', we have also 5 star, the angle OB'C congruent to the angle OC'B. From 4 star and 5 star, we obtain the congruence. The angle OAD' is congruent to the angle OB'C, which shows that CAD'B is also an inscribed quadrilateral, and hence the congruence 6 star angle OAB' congruent to the angle OD'C is valid. From 2 star and 6 star, it follows that the angle OBA' is congruent to the angle OAB', and this congruence shows that BA' and AB' are parallel as Pascal's theorem demands. In case D' coincides with one of the points A', B', C', it is necessary to make a modification of this method, which evidently is not difficult to do. The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice: this ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Wrenholt. Programming and illustrations by Jim Wrenholt. 2019. Portrait of David Hilbert by Reida Wrenholt. Thank you for listening.